Let's start with electrostatics. So, first few things is that just like whenever there is a mass in space, let's say this is space and there is a mass. This is space and there is a mass in the space, then it will produce some gravity in the region. Some it will release some gravitational field. It will have some gravitational fields. It will produce some gravitational field in space, and it comes out of the mass and goes outward away from the mass, and it goes out at the speed of the light. This gravitational field which is released from the mass, it is released from the mass and it travels the speed of light, c, which is 3 into 10 to power 8 meter per second approximately. So the fields which and these fields which travel at the speed of light, these gravitational fields, they when interact with any mass. Let's say there is a field coming here and there is some another mass, let's say m1. Then these fields and this mass, these two interact, and there is a force acting on the mass. When we deal with statics, then these fields do not seem to travel because these field values do not seem to change because let's say that there is a mass m here and there is, let's say, point p at a r distance. So the gravitational field is gm1 m2 upon r square. That's the field value at here. This field come out and travel away from it, and their strength depends on the density of the field. Let's say this whole field was concentrated at this small point mass, but when it spreads out, it spreads in the area 4 pi r square. The area of the whole sphere would be 4 pi r square. So since the more is the area, the lesser is the density. So we can say that the density of field is inversely proportional to area of the surface, which is 4 pi r square. So we can say that the density of the field is inversely proportional to r square, and the density of the field is directly proportional to that the the force which acts the force which acts, let's say, is g. Let's say there is a mass m1 and this is mass m1 and this is mass m2. Then the force acting at this point would be this, and this force would be directly proportional to 1 upon r square, and this force is directly proportional to the density of this field coming out. So we can think like that. The reason for the inverse square law can be like this, that the density of the field decreases as the inverse as the area of this surface increases, because the density because the quantity of the field released, let's say with the same phase, quantity of the field released at a time is fixed, and when it spreads out, it gets spreaded over whole area, so the density of this field will become less, and the lesser is the density, the lesser is the force, because force is dependent on the density of this field. and this field applies force. Now what happens if I move this particle suddenly from this place to any other place? Then what would happen is that since this field travel from this mass at some speed c, in case of statics they don't seem to move because they are always released from this fixed point and they are already released. We are assuming that this field is already released much long ago, and as these fields are released they have already reached to the infinite positions, means they are already tending to move to the infinity. So field is set in space all over the space already. In case of statics we assume that field is already set all over the space, in space. But in case of, let's say, when I suddenly move this particle from one place to another, then from this new position, let's say this distance will become r2. So from this new position the wave will release and reach this point, and this, and the time taken for this to happen would be c by r2, which is the, sorry, r2 by c, which is the distance upon speed. After this time the field from this point will reach here. So the new field, according to this equation, according to this position, which would say that the force is equal to g m1 m2 upon r2 square. This force would be felt after time is equal to r2 by c. So this would be the time taken for this new force to occur. But since the speed of light is too high, that this time is almost approximately tending to the zero, very small value becomes of this time. And during this process of moving, the field value here will remain. Let's say this field this distance is, let's say, r, and so the distance divided by time is r by c. So when this mass is, let's say this mass disappears, now in this, let's make another case and say that this mass has disappeared. So if this mass disappears, there would still be field here, and the field would be felt here for time is equal to r by c. For this long time there would still be some field here felt, because this field is traveling, because this field is released by this mass, and even if it disappears now, the field up to this length, this will travel and apply force on this point. So without this mass there would be some force acting on this particle for time is equal to r by c. So this was the concept of these fields. Similarly, this happens in case of electrostatics, electric field also. Let's say there is a charge q1. Whenever there is a charge q1, it releases some electric field, and field the field value is directly proportional to the density of these field lines. These are field lines. Density of these field lines, electric field at any point is directly proportional to the density of the field lines, and we know that the whole field lines released from this point, after they spread out to a radius, let's say r, they will be spreaded into a area of 4 pi r square. Means the number of field lines per unit area would be inversely proportional to the total area 4 pi r square, because the number of field lines is, let's say, n, and the more is the area, the lesser is the density. Density is simply area and number of field lines. So number of field lines would be, so density is inversely proportional to r square. So therefore electric field is inversely proportional to r square. This can be one logic. Now, now all those, these field also travel with the speed of light. These field also travel with the speed of light. Means if this, let's say there is a charge q2 here, there is a force q1 k q1 q2 upon r square acting on this charged particle. Now if this charge disappears, let's say at time t is equal to 0, this charge disappears. Now if it disappears, there would be still some field from this point to this point, which will be traveling now at the speed of light. And since this distance is r, since this distance is r, this point will take r by c time to reach this point. And up to this time r by c, there would be force acting on this particle equal to this force will act on this particle q2 charge uh, for r by c time, because the force is due to the fields. Force is due to interaction of field and charge. So there is, this field is coming, charge q2, force on q2, force on q2 is due to the interaction of field of q1. Q1 has released some field, and the field is still present even after it disappears, and it is present for r by c time for this q2 charge, because after that this field will go away, and there would be no field in this region after that time. So as long as these fields are present around this q2 charge, there would be force acting on this q2 charge. So in case of electrostatics, what we mean that what we mean is that the charge is at fixed location, neither it is disappearing, nothing is happening here, and the even if the motion happens, that would be very slow, so that the time will be approximately zero for any phenomena. Now in case of electrostatic, let's simply start with our formulas for field. Formula for field. So first thing is, when there is a straight line of charge, when there is a straight line of charge, let's say from this point to this point, it is, let's say, lambda density of charge. it's it is uniformly charged, uniformly charged it is uniformly charged with lambda charge density. And let's say there is some point here from which there is, we are taking another point from which, let's say we are taking a point in the space here p, on which we want to calculate the electric field due to this charge density. So what we will do is that we will draw a perpendicular line here. The distance of this perpendicular line would be, let's say, r. Now we will say that now what we need is that the angle of this, let's say theta 1, and the angle of this, let's say theta 2, and we should know the direction of, we should know how to take the direction of this theta 1 and theta 2. Theta 1 in this direction is taken from this line towards this. Just like we take a positive x-axis and then there is an angle, we take angle like this. Similarly, we will take angle from this axis, from this positive direction, so the angle will be taken like this and taken like this. For theta 2 the angle would be positive in this way, and for theta 1 the angle is positive in this way. So if the point is like say here, and this is the line, I will extend this line. Let's say the line is from, the charge line is from A to B, but I am extending this and the perpendicular distance would become, let's say, this r. Now theta 1 would be the angle from this to this, let's say theta 1, and this angle would become from this line to this line, this is theta 2. This was supposed to be in this direction, but I have wrote in this direction, then this value will be taken as negative. This theta angle will be taken as negative, while this theta 1 will be taken as positive, because one angle is positive in this direction while other is positive in this direction. So these are theta 1, theta 2, and this is the length from this line of charge perpendicular to the point P. If point P is here, then we will take the perpendicular distance from this extended part. So the formula for the electric field, there would be some field. Let's say this is a positive charge density. If I am assuming that it is positive charge, then there would be some field in this direction. This is called E perpendicular because it is perpendicular to the line. This is the line of charge density and it is perpendicular to the line of charge density. So the electric field perpendicular would be in this direction, and there would be some electric field parallel to this line, because there is some more charge here, there is some less charge here, so there would be some net force probably acting in this direction or in this direction, depending on which side has more charge. So there would be two types of field for this finite length. This is finite length, finite wire length, charged wire. Now in this case we get the E parallel. We call this the line, we call this field parallel, E parallel, because it is parallel to the line of charge. So since it is parallel to the system of charge, we call it E parallel. And this E parallel, this E perpendicular is simply given by K lambda by R sine theta 1 plus sine theta 2. This is perpendicular to this, and the direction can be simply found by knowing the charge type. If it is positive, then it will point away from this, and if it is negative charge, then it will point toward the let's charge wire. Now E parallel. E parallel is given by K lambda by R bracket. Let's say I am taking field. The formula will be like, if the charge is more in this side, then the field would be more in this side, and if the charge is more in this side, then this angle would be greater. So cos theta would be smaller. So cos theta would be smaller, means if I want to use cos theta 1 minus cos theta 2, let's say I am taking, this is the direction of the field, then this is theta 1 in this direction, then I will say the formula will become cos theta 2 minus cos theta 1 Here it is small and it is large. This value will become positive and the field is in this direction. So it will become n theta 2 cape. In this direction would be the field. Means since this angle is small, this value would be large and this will become positive, and we know that if this side is small, this is large, then the field will be in this direction. If this is positive, if lambda is negative, the field will automatically get reversed. So the angle from which I am subtracting cos theta 1, I will take the same as unit vector. This unit vector, let's say n theta 2. This unit vector n theta 2 means a unit vector in this direction of theta 2, in this direction parallel to the line in this theta 2 cape. And n theta 1 cape means a unit vector in this direction along a line parallel to the charge density charge line and in the direction of theta 1. And this theta 2 would be, and theta 2 would be, and theta 2 cape would be in this direction of this angle. So the angle from which I am subtracting, I will take the same theta unit vector here. I can also write it as k lambda upon r cos theta 1 minus cos theta 2 and theta 1 cape. Negative of this become negative of, when we take negative of this, the negative sign comes out, and multiplied by this will give n theta cape, n theta 2 cape. So the formula will look like this. So this is the formula for field to this line charge. And let's say this let's say I want to find a field at another point, let's say P here along this line. This field was at any line which was at some distance from this line, some perpendicular distance from this line. But if I want to find the field at its line, a point lying on its line, then the field would be found as, this field would be equal to this. Let's say this length is L, and let's say this length is A. Then if the total charge on this line is Q, then the field would be KQ upon L plus A times A. This will become the formula of the field for the field at the point P, which is along the line. This is KQ upon L plus A times A. In terms of lambda, we can write K lambda L upon L plus A times A. So we will write it properly one more time. We will write it in proper manner, that if there is a line here, finite line here, at any point, P here, or at any point, let's say P days here, the electric field at this point and the electric field here would be, this is the perpendicular and this is, let's say, a parallel, and you will join these lines and a perpendicular distance here. This perpendicular distance is r, this is, let's say, theta 1, and this angle would be theta 2, and it has lambda charge density and total charge Q and total length L. From this point to this point, the length is L, and from this point to this end, the length is a, then the field at this point EP dash is equal to K Q KQ upon L, sorry, L plus A times A, and the this is E parallel. E parallel is equal to E parallel is equal to K lambda upon R cos theta 1 minus cos theta 2 in the direction of n theta 1 k, while E perpendicular is equal to K lambda upon R sin theta 1 plus sin theta 2 only, and the direction can be simply found by knowing the sign of the charge, or we can say that the field is pointing away from the line. If lambda is negative, the unit vector will get reversed. Let's say the n vector, this is an perpendicular vector which is pointing away, we will multiply simply with n perpendicular vector, unit vector. Now the second thing is, these are formulas. Now the second case would be field due to an arc. Field due to an arc. The field due to an arc. Let's say there is an arc in the space. It has lambda charge density. Here k is equal to 9 into 10 to the power 9. The constant used in Coulomb's law. Let's say there is an arc, and this arc is made by a radius r. This arc is made by a radius r, and this angle is, let's say, alpha. This arc is made by a radius r, and it subtends alpha angle. Now from this arc, let's say this was a circle, this was part of a circle, and this is the center point of it. An axis passes from the center point perpendicular to the plane of the arc. This axis is perpendicular to the plane of arc. Now if I take any point here, let's say P, then this point P, if I join it with any line here, if I join it with any line on this arc, if I join this point with any point on this arc, then this line and this point will make some beta angle. It is same for all. It is same for any point. This point when joined with this point will again make beta angle. For all this arc, there will be some beta angle made. So I will simply write it as the angle I made is beta here from this line and a line joining this point P and this arc. Now I want to find, now I know that there would be some field in this direction, there would be some field in this direction. The total field at this point can be represented as the sum of these two fields, and this field, since it is the plane of this arc is this and it is perpendicular to this plane, we will call it as E perpendicular, and since this is parallel to the plane of the field, we will call it as E parallel. Now again here we have a formula for this E perpendicular and E parallel. This was for a line and this is for arc. The E parallel, the most important is E perpendicular. E perpendicular is given by K lambda upon radius r times alpha. This E perpendicular is K lambda upon r times this alpha angle multiplied by sine square of beta and cos beta. This is the formula for E perpendicular, and this is E parallel is equal to k lambda upon r times sine cube beta, sine cube beta times 2 times of sine alpha by 2. So the formula for it is like this. The alpha terms comes in this perpendicular like this, and in parallel case like this. So the formula for these two is like this. Now if this arc becomes a complete circle, this alpha will become 2 pi, and in case of 2 pi this E parallel will become 0. For a complete circle this E parallel will become 0 and there will be only perpendicular field. So these were two formulas for field due to, let's say, this perpendicular and parallel. And now in this case, for this E perpendicular, when this equation is, we know that if the point P is variable, we want to find the point P where this value of E perpendicular, we want to find the point P where the value of E perpendicular is max. Let's say this distance is x, then for E perpendicular to be max, x should be either plus or minus r by root 2. This is the radius. When this distance becomes r by root 2, either in this direction or in this direction, the E perpendicular will be maximum. The graph for E perpendicular looks like, the graph for E perpendicular looks like this. This is the position x and this is the perpendicular E. The field value increases then decreases. So the field value increases and then decreases like this, and this max value is found at r by root 2, and then it in the opposite direction, the field direction changes, becomes max, and then like this, the field value is max again at minus r by root 2. So this was the equation for, this was the graph for E perpendicular with x-axis. And these are some important points here. Now moving ahead to other formulas. This arc formula can be used for any part of circle, which can be quadrant, semicircle or whole circle. We can calculate all these field values from this simple arc formula. Now the another case is of, let's say there is let's say a disk. There is, let's say, a disk of, let's say, radius r. There would be disk, it would have some radius r, and let's say there is a perpendicular axis from the center, and any point P is here from this disk. This point P is making from this circumference, we choose any point and join this with the point P. The line made by this axis and this line, this, let's call this beta again. We will call this beta. Now what happens, that there would be some field here. There is some sigma charge density. This is areal charge density per unit area of this disk. This is sigma. Then in this case, there will be some E perpendicular here. Since this field is perpendicular to this plane, then the E perpendicular, there would be only E perpendicular here, and the E perpendicular would be equal to sigma upon 2 epsilon bracket 1 minus cos beta. This is the formula for field due to this disk of charge. And when this disk becomes very large, or this point becomes very close to it, the beta angle tends to become 90 degree, and as it becomes 90 degree, this will become sigma upon 2 epsilon only. So the field of perpendicular would become sigma upon 2 epsilon when this either becomes very large or this becomes very close. The beta angle becomes approximately 90 degree. So this was the field due to this. And similarly, if there is any area, this is any plane surface, flat surface of this is any flat charge density, flat plane of, this is a plane, flat plane of sigma charge density. Then at any point which is very close to this, any point which is very close to it, let's say this is infinite, this is tending to the infinity, this is very large area, very large plane, this is infinite flat plane, then the field at a point P here would be equal to, the field would be equal to, this field will be perpendicular to the plane, this field will be equal to sigma upon 2 epsilon. Now note here that I am writing epsilon, not epsilon naught. So epsilon is dependent on the medium here. So if the medium has a dielectric constant, let's say K, then we will write E equals to K times of epsilon naught. So we have to write epsilon according to the medium. If medium is a vacuum over here, then it would be epsilon naught. If it is water or something else, then we will multiply by the dielectric constant. Epsilon naught into dielectric constant, this will become the value of E. Now, the fifth case is if there is a uniform charge density of rho, and there is a, let's say, center here, and then I want to find the field at any r distance from it. This is an r vector. There is a point P here. It has some, it is a distance vector r from this center, let's say O. Then the field at this point, this field, electric field at this point is equal to, this was for infinite plane, this was for infinite plane, and this was for disk, and this is for solid, uniformly charged solid. So this is for charged solid, and its formula would be rho r upon 3 epsilon. So epsilon depends on the medium of this body, and r vector tells in which direction the electric field vector points. And it is only valid, let's say this radius is r, valid up to, it is valid only up to r equal to r, valid for r less than or equal to r. So the radius vector we have chosen, it should be inside this whole thing. Only then this formula would be used. And if the point taken is outside, then the formula of field will simply become kq over r square. This will become the equation of electric field if r greater than r. And now we will need some more formulas. For example, field due to dipole. So in case of field due to dipole, let's say there is a dipole. This is maybe sixth, seventh part. Field due to electric dipole. So electric field due to a dipole is given by, it has, we can make few cases of it. First case would be field in equatorial plane. Field in the equatorial plane. Field in the equatorial plane, let's say this is minus q, this is some plus q charge, and this is a dipole. It has center here a, o, and this has length a. Then in this equatorial plane, let's say there is an r distance, the point p is at any r distance, then the field would be equal to, in such case the field will be equal to the dipole moment, the electric dipole vector p points in this direction from minus q to q. This is the direction of p vector. So the formula of field will be, since this positive charge releases, field it goes in this direction and comes in this direction and annihilates in this negative. So the field would be opposite to the dipole moment vector. The formula for electric field would be minus k p vector into r divided by r square plus a square to the power 3 by 2. This is the formula for field due to field in equatorial plane at any point in equatorial plane. The second thing is field field along axis outside the outside dipole means this was the dipole, this was our dipole, and we were taking field at this point. This was the field. In case of dipole and the field outside, let's say this is again minus q, this is o, this length is a, both lengths are a, and this is plus q charge. The dipole moment points in this direction, and I am taking a point along this line. I am taking a point along this line. Let's say at this point P, I want to find the electric field. So this length R is obviously greater than this A length, and the point P is outside this dipole. It is not, the point cannot be inside. We are not taking any point inside this dipole. We are taking the point P outside and along the axis. So in this case, the electric field would be 2k p over r square minus a square whole square. But there is also a third case. There is a third case when the point P is taken inside. In the third case, field along axis inside dipole. We can derive this inside dipole. We can derive this formula simply. Let's say this is deriving here. This is the dipole. This center. This is minus q charge. This is plus q charge, and let's say there is a point here. This length is r, and this half length of this dipole is a. Then the field at this point, this will make field in this direction, and negative charge will also produce field in this direction. The field value will be, electric field will be equal to k q upon r. Due to negative charge it would be a plus r square, r plus a whole square, and due to positive charge it would be a minus r square along and in the same direction, a minus r whole square. This becomes kq upon r square minus a square whole square. Taking a square minus r square, we get here 2 times of r square plus a square. So the formula of field will become this: electric field is equal to, since we are talking about a dipole, it would be better to write it in the form of dipole. Let's say this is multiplying and divided by a. 2qa will become dipole moment. So dipole, electric dipole. So we will get formula kp upon a r square minus a square whole square. Since we are taking the whole square, the order doesn't matter in this, and the value above would be r square plus a square, and the direction of the field is negative to the, so the field equation will become this. So these are the three formulas of the dipole. Okay, now moving ahead, how to memorize. Simply that in the case of field x on the axis outside dipole, we have r square minus a square whole square and 2 times, while in this case we have similarity with this minus kp vector, but here the formula both have same things, only this r square plus a square is different, and we can derive it on the spot also. We don't need to memorize it. Now the next part of the electric field, about we'll talk about torque and other steps. Let's say there is a uniform electric field. Uniform electric field means it is pointing in the same direction, and its magnitude is same everywhere. So let's say there is some electric field here in this direction. Its magnitude is a all over everywhere, and direction in this direction. I place a dipole moment, dipole electric dipole here. Then in this case, there would be some torque acting on this dipole. Let's say torque acting on this dipole is tau when it is making. Let's say this is the vector of dipole as this, and this is the field direction. Then the positive direction of both vectors will make this theta angle between them. Then we have the torque. The torque is equal to P cross E. This is the formula for torque. And the small work done. If this dipole, since this for this dipole, if we see there is a negative q charge here and there is positive q charge here, this whole system has F net equal to 0 because electric field is applying F force in this direction and F force in this direction. The net force on this system is 0. There is only some torque acting on this system. Now the torque acting on the system is this P cross E, and we can now calculate if this is a rigid system. Let's say if there is a rigid body here, it has some moment of inertia about center I, then we can calculate the alpha of this body would be torque divided by this moment of inertia, which is P cross E divided by moment of inertia. This will give the alpha. And when there is a torque, when there is a torque and the dipole moment vector is rotated, this dipole is rotated, then the work done is tau d theta. Let's say it is rotated by d theta angle, then the dw work, the work done in case of rotating it is equal to the tau d theta. Since this tau is due to the field, this is the work done by E. This is also by electric field and this is also by electric field. So the, let's say the torque is acting like this, trying to move it, trying to align it in the direction of the electric field. Then when it rotates by d theta angle, the torque and d theta are positive. They positive dot product and the work done by the electric field is positive. And since this is a conservative force system, this is conservative, since this is, since force acting on the charged particle is constant at all locations, then it is a conservative force system. We can say that the, we can talk about potential energy stored. So the potential energy change in this case would be equal to minus dw by E. So the potential energy change of the in this electric field would be equal to the minus dw by E. So we get the delta U is equal to integration of this tau d theta, which gives Pe cos theta 1 minus cos theta 2, where theta 1 is the final angle and theta 2 is the initial angle. This is the change in potential energy. Now if I want to talk about the potential energy at any angle theta, then it would be equal, then I will assume that, let's say I will have to tell the potential energy at any point, at any angle. We have to take the reference potential energy. So I am considering that when theta is equal to 90 degree, the potential energy is equal to 0. This implies that potential energy at any angle theta is equal to minus P dot E, which is Pe cos theta minus Pe cos theta. Is it right? When it is 90 degree, something is wrong or right. And this is the potential energy of this. Due to this rotation only, there is also some rotation. I have taken the potential energy when this dipole was at 90 degree. When this dipole was at 90 degree, I have taken it as, it has This should be a positive sign here. Maybe. I need to check if this is negative here or not. Since we know that when this charge rotates from this point to this point, there should be a uh, there should be a negative sign here because the work done by the gravity is negative. So P cos theta final minus P cos theta initial, we will have a negative sign here too. So now this is correct. And we taken theta initial as 90 degree, theta 90 degree. When theta is at 90 degree, then u is equal to 0. But when the theta is at 90 degree, this dipole has its own energy also, because there is a plus q charge here, there is a minus q charge here, there is some potential energy due to their separation also, which is equal to, I guess, kq by r times minus q, kq square by r. If there is a this is 2a, their length between them is 2a. So there is some potential energy due to the system. There is some fixed potential energy of the dipole itself, which is minus kq square by 2a. And there is some potential energy due to the electric field outside also. So these are few things. Now moving ahead, we have completed all the steps about electric field here. One more formula for electric field would be one more formula for the electric field. We have talked about the field due to arc, straight line, disk, infinite plane, and due to uniform charge density, solid sphere inside it. And now one more formula for electric field. Let's say this is its formula. Maybe the formula, let's say there is a sphere, there is a sphere of sigma charge density at its surface, hollow sphere. This is a hollow sphere and has sigma charge density at its surface. Now I cut a cross section of it, and I cut out a part of it. Let's say I take this part outside, I cut this part and take it here. This is the part of this sphere which I have cut, and let's say this was the center of it, and its radius was r, and this was the axis through it. I have made a line symmetrically passing through this sphere from its center point. Now in this case, let's say this whole part makes a angle theta. Let's say this whole chord, this is the center, and this whole angle, let's say, is theta. I have cut out this part here, and this whole angle, this is planar angle, not solid angle. So it is a 2D angle. So it is making theta angle here in this case. Now in this case, the field would be, let's say this is r, and the sigma is the charge density. Then there would be some field here. Since it is acting perpendicular, I will call it E perpendicular. Then the formula for the E perpendicular is equal to pi times k sigma sine square theta by 2. This whole angle is theta. This whole angle is theta. Then the half of this theta into sine square of this half of the angle times sigma into k pi. This is the formula for the electric field due to this. When this becomes a complete sphere, when this theta becomes 2 pi, this becomes 0, and so the electric field also becomes 0. So this is the electric field. This is the part of sphere, part of hollow sphere. Field due to the part of hollow sphere. And this is the field at center O. This is the field at center O. One more formula we need to remember sometimes in case of calculation it may help. That is for this part which makes, let's say this angle is theta, and this radius is, let's say, r. Then the area of this part is a is equal to 2 pi r square bracket 1 minus cos theta by 2. This is the formula for this area, or this can also be written as a is equal to, let's say, this length from this point to this point. The length is a, means that this r would look like this if you see from this side, and this was the cross section of cut. This was center of this, and if I join it by a line here, this length I will call it as a. This length is a. Then the area of this part is 2 pi r a, and let's say this I have cut this part length is a, then this part length would be 2r minus a. The area of this part should be, this part would be 2 pi ra, and therefore this part should have area 2 pi r bracket 2r minus a. It gives 4 pi r square minus 2 pi r a. This two can cancelled. The total area becomes 4 pi r square. So we have verified also this formula. Now this was electric field.